All right, I'm going to start, Phil.
Go ahead.
All right, welcome everyone to tonight's presentation of integrating renewables into the grid. The MAREA group, the Mid-Atlantic Renewable Energy Association, provides educational and informative presentations like this and other educational experiences on renewable energy and sustainable living. Coming up in August, we have a presentation from electric vehicle owners. They're going to talk about the challenges or what's changed. You know, lots changed in electrical vehicles over the last several years. So they're going to talk about their experiences, not only in driving and charging, but also those that charge their vehicles at home with solars. So look for that end of August, and actually August 30th at 7 o'clock. And then finally, if you want to learn more about these presentations or other upcoming presentations, go to the MAREA.org. Or if you want to contribute to the MAREA, if you want to help with presentations or whatever that might be, or suggestions, go to the MAREA.org and click on contact and send us a message. We'd like to hear from you. Phil, you want to start tonight's presentation?
Okay, thank you. Welcome, everybody. During the presentation, if you could please mute your microphones and enter your questions into the chat box. At the end of the presentation, we will ask your chat questions to the presenter. Tonight's presentation will be recorded. At the end of the presentation, there will be, and the end after the question and answers, there'll be an informal connection session for those in the audience who want to stay in the Zoom session to chat about the presentation or related renewable energy and sustainable living topics of interest. We hope you'll join us. Now it's time to take you to renewables on the grid. We're pleased to have tonight Dr. Ben Kroposki, is the director of the Power Systems Engineering Center at the National Renewable Energy Laboratory, or NREL, where he leads NREL's strategic research in the design, planning, and operations of electrical power systems. He has over 30 years of experience in the design, testing, and integration of renewable and distributed power systems, and has more than 150 publications in this area, with over 9,000 citations. Dr. Kroposki received his BSEE and MSEE from Virginia Tech and PhD from the Colorado School of Mines. As an IEEE fellow, Dr. Kroposki was recognized for his leadership in renewable and distributed energy systems integration. Dr. Kroposki is also an adjunct professor at the Colorado School of Mines and the University of Colorado, and he teaches courses on integrating renewable energy into power systems. Welcome, Dr. Kroposki.
Okay, thank you very much for having me here today. I'll go ahead and get started. So let me first, I'm just going to turn off my video to save some bandwidth, and then I'll switch over to screen sharing of my presentation. And hopefully everybody can see that. So today I am going to talk about integrating massive amounts of wind and solar into electric power systems. And to step back and take a look at what is actually happening in our power system today, because the US energy supply is going through a pretty monumental shift. And it's important to understand what's kind of going on. From the 1950s to roughly 2010, there was this very steady upward growth in the amount of electricity being used in the United States. And starting in around 2008, 2009, when the Great Recession started, we started seeing a pretty big change. So since 2010, over the last 10 years, coal has gone through a significant decline in terms of the overall amount of energy produced. And that's being backfilled with natural gas and renewables, and those have increased tremendously, while nuclear and hydropower have remained pretty steady. In fact, the year 2020 was a pretty seminal year in terms of energy supply in the US. And it was actually the first year that renewables, and renewables including hydropower, produced more energy on an annual basis than either nuclear or coal in the United States. So something pretty big happening. So let's take a look at that 20% of renewables. You can see in this small graph on the left, 2020 was also seminal in that it was the first year that wind actually produced more energy than hydropower. So hydropower's remained fairly constant since about 1980. Over the last 40 years, we haven't built a drastic amount of new hydropower in the United States. But the thing that's really happened in the last 10 years is a massive deployment of wind technology. And then maybe in the last 5 years, solar technologies. So why is all this happening? There's really two big drivers for this in the US. And first is economics, because economics are going to drive everything. It's really what's sort of held up renewables in the past. And if you take a look at the cost curves over on the left-hand side, you can see in the last 10 years that utility scale wind and solar plants are now the lowest form cost of new electricity. So what that means is if you're going to build a new plant in the United States, these are nominally average values. And of course, it does depend on if you have relatively good wind or solar resources. But if you compare that to even a new natural gas plant or coal or nuclear, wind and solar are right now the lowest form cost of new electricity. So that's really driving the push towards wind and solar at scale. Now, of course, you do have the challenges with the variability of wind and solar, and I'll talk about that more in the rest of this presentation of how to deal with that variability. And if you look at the right-hand side of this graph, you can see a map of the United States with a bunch of coloring on it. The colors are different aspects of state and utility decarbonization commitments. But what this means is that you have individual states, you have the irregularly shaped areas or the utility service territories, all that have developed some level of decarbonization commitment, whether it's 100% decarbonization by 2050 or some version of in between there. But you can see a large portion of the United States is also pushing forward with state or utility service territory goals and targets. So we don't have a national target for the United States, but you can see probably at least 75% of the US has some sort of target. Now, as we sit and think about where are we heading with this transition, the new Biden administration has a goal of getting to 100% clean electricity in the United States by 2035. That is less than 15 years away to convert all of our electricity use in the United States, so everything you saw on the previous slide, to clean sources. And if you kind of think about, okay, we have 20% of our energy being provided by the nuclear fleet, we expect that to continue operation, 7% from hydro, and maybe some amount being provided by maybe clean hydrogen fuels or carbon sequestration or something. It still means that you're going to need roughly 50 to 70% wind and solar on an annual energy basis. And those are some pretty big numbers. And if you compare to where we are today, last year in 2021, wind and solar provided 13% of US electricity. So it's gone up considerably in the last 10 years. But we need to migrate from around 13% to over 50% on an annual basis, which is a significant change from where we are today. Another slide that I put in here is sort of what does that long-term transformation of the power system look like? And these are some studies that we've done at NREL. You can see the source down below, but that look out to say 2050. If we were to have a completely clean energy system, what does it mean? It means, you know, a massive decline in the use of coal and of natural gas, and much greater increase in solar photovoltaics or PV, as well as wind and batteries. And the key thing to take away from this is these are really big numbers. If you were to look, if you can look at the left-hand side of that graph and you see where the 2020 number is, that's around 1,000 gigawatts of total installed capacity. That's all of our generation fleet today. And then if you go to the right-hand side, the 2050 number, you see that that's over 3,000. And what that's basically saying is we need roughly 3 times the amount of installed capacity that we currently have today. That is a huge growth in solar, wind, battery technologies over the coming decades. The other thing that's interesting just to point out here, and we'll touch on this later in the presentation, is that batteries, PV, and wind are all what we call inverter-based resources. They use a piece of power electronics to create their AC waveform and connect to the grid, while coal plants, hydro plants, nuclear plants, and natural gas plants all use synchronous generators. Now, I'll just point out that that's a difference, and I'll get a little bit more into the difference later in the presentation. Okay, so those are some pretty big numbers. So what do we know about operating power systems with variable generation? So these slides coming up here kind of discuss that kind of thing about what do we know today and how is this going to change into the future. So people may be surprised to realize that we actually know how to run and develop reasonable sized power grids with 100% renewables today. And so here's some examples, but I would consider these small examples of power systems. And 2 important numbers to realize here: the red square, that number is what we call an instantaneous level, and the gray circle is an annual level of renewables. So the difference between the two is that instantaneous number is any point during a year, whether it's 5 minutes, 15 minutes, an hour, that's the peak level at that point in time. Whereas the annual one is over the entire year. So as an example on these small island power systems, and then if we look along the bottom, you see system size, that's in gigawatts. So just to give you some context, we're talking right now about systems that range from hundreds of kilowatts to around 10 megawatts. And then as the middle of this graph, we'll see some other systems or gigawatt size. The entire continental United States is 1,000 gigawatts, so all the way to the right-hand side. Some important things to know about these small island power systems. When we design them to run on 100% renewables, we have to overbuild the wind and solar because the capacity factor or the amount of energy production, is limited to when the resources are happening. For example, solar power, solar sun is only during the day. We have to add energy storage to run those systems on night. Or we have to have some type of energy storage, including batteries, or as you can see in the case of El Hierro on the right-hand side, you see a pumped hydro system on that island. But as you can see here, we know how to run 100% instantaneous levels and very high, over 50% on annual basis. So again, we know how to make small island power systems operate with large amounts of wind and solar. As we migrate to a little bit bigger systems, these are systems that look like power systems that you would run into in the real world. They have a transmission system, a distribution system. They have generation scattered throughout the island. They have control rooms where you have system operators controlling the power flows. And so you can see some examples of the Hawaiian Islands. In case you hear any background noise, I'm in the middle of a giant thunderstorm right now. But we'll let that hopefully pass safely through. You have Maui and Kauai as examples where they are fairly high instantaneous levels and up to 40% on an annual basis. And then a much larger system like the entire country of Ireland, that's around a 6 gigawatt system. It is up around 65% instantaneous and 30% on an annual energy basis. That's mostly a wind system. So some recent, if you take a look, this is 2019 data, some recent advancements are that Maui, we've been actually working with the Hawaiian Electric Company, and they've gotten instantaneous levels up to basically 90%. And similarly, Ireland just recently, as last year, was up at 70% on an instantaneous level. Again, key thing here is those two numbers, and we want to get the gray numbers above 50 and get the red numbers up as close to 100 as possible. As we move to slightly larger power grids, these are things, in case you don't realize this, in the United States, we have three main power grids. There's a thing called the Eastern Interconnection. There is the Western Interconnection. You can see it outlined in the middle, and the Texas Power System, or ERCOT. And this gives you some numbers of those systems. But the ERCOT system, the smallest of those, it also has some fairly high levels of wind and solar deployed in it. And in fact, last spring, they were able to get up to 66% on an instantaneous level and around 26% on an annual level for their power grid. So as we take a look at all these power systems, the key points here are to realize what we're trying to do is get those red numbers up to near 100%. And that will enable us to be able to deploy more and more of the renewable technologies and increase the annual energy levels. A couple other graphs just to show that this is not just an island power system phenomenon that we're talking about. This is actually happening right now in real time across the United States. And you can see this particular graph is for a place in the United States called the Southwest Power Pool. That is this middle section of the United States right in here, where there's a heavy amount of wind deployed across the middle of the United States. If you take a look at this graph, this is showing blue is actual load. So this is thousands of megawatts. And then the red is the forecasted load. And this is for earlier February of this year. And then the green down here is predicted wind forecast. But you can see there's a point in time here where they were predicting they would be able to have 100% of the native load inside this entire service territory being provided by wind. Now, that didn't actually happen. They actually curtailed the wind at about 80% of that load. And I'll get into some of the reasons behind that curtailment as we go on here. But just to realize this is, a coming attraction of everywhere in the United States. And if you take a look at the queue, or the amount of generation that is planned to be put into the SPP service territory, they currently have roughly 30 gigawatts of wind. They are planning another 30 gigawatts of wind and 40 gigawatts of solar. Right now, they have less than 1 gigawatt of solar. That's these little bumps down here on the bottom. If they were to really deploy 42 gigawatts, what that would look like is something like this in terms of solar output every single day. Now, the nice part about Southwest Power Pool is that the solar resource and the wind resource do a very nice job of complementing each other, meaning it's windy at night and the wind tails down in the day. It's not always like that, but it's a pretty nice way of connecting wind and solar. The bigger challenge is when they deploy this 30 additional gigawatts of wind. Basically, if they were to do that in the same locations that they currently have systems, that would raise the amount of generation up here, and it would always be over the amount of native load. Now, in SPP service territory, they can sell that energy to the neighboring service territories. But realize that, in general, we're starting to see this massive deployment of wind and solar. There's stuff getting ready to be installed. It's in the queue. And so it's going to be happening over the next basically 10 years of deployment. We're also seeing this happen around the world. So this is an example of South Australia. Now, if you take a look at Australia over here on the left-hand side, South Australia is this piece of it that's a kind of equivalent to a state in the Australian grid. They have already had, in October of 2020, an example of a day where 100% of the native load was provided by solar. So this red line across here is the native load. And we can look between 12:30 and 2:30 that day, 100% of that native load was being provided by solar. So this is distributed or rooftop solar in the light yellow, and then utility scale solar in this darker yellow. But they also kept some natural gas plants up and running. And they were basically exporting this to their neighbors, New South Wales. So native load wise, they were able to provide 100%, but they still were maintaining synchronous generator, natural gas plants for operational stability. And I'll talk a little bit more about that challenge that we have coming up. So as we're trying to, again, take these systems to higher levels, what we need are new technology solutions to get these inverter-based instantaneous levels up to 100% at all times so that we can shut down the natural gas plants. We don't have to have them running for additional stability concerns. And we'll get into that here in a second. In fact, one of the things that we're very much trying to work on now is unifying the integration of inverter-based resources and synchronous generators. So how do we get to very high instantaneous levels of inverter-based resources? So a little lesson on the power grid. Right now, our conventional generation fleet, hydro, nuclear, coal, natural gas, they all burn fuel or move water through them, but all of them are spinning something called a synchronous generator. And the reason it's called synchronous generator is because they all can synchronize together and run at what they call synchronous speed in such a way that they produce output AC power that makes a 60 hertz waveform in the United States. Now, this is sort of a mechanical representation of what's happening electrically, but when we electrically intertie two generators together, they basically synchronize together and operate as a large virtual machine. And when we connect things like induction machines or inverter-based resources, they don't necessarily have that same physical characteristic as a synchronous generator does. But the nice part about generators in general, when they're synchronized together, if we were to lose one of these generators, other generators online would instantaneously pick up the slack and keep this system operational. Now, what we want to be able to do is create inverters in the wind plants and in this PV plants that replicate some of those very fast conditions and basically replicate some of the response characteristics of synchronous generators. So it's really this idea of creating inverter-based resources that in some ways mimic the properties that we would see in synchronous generators. The challenge is it's not always possible to mimic all those properties. An example of why we would want to do that, if you take the Western United States here, this is an example of where we have deployed, in this case, roughly 30% of the native load provided by wind and solar. And some of the wind plants and solar plants have these smart inverter capabilities about regulating voltage and frequency. And what you'll see in this little demo here is that each of these dots represent a voltage level. You want them green, obviously. So if they go red, that's causing an issue. And then the other thing that we want to pay attention to is the system-wide frequency. So inside the Western Interconnect, all the synchronous generators are interconnected together and operating at 60 hertz and synchronized together. When a fault happens or a loss of generation or a transmission line goes out, you have an event occur, and you'll see that in the system frequency. So what we're going to do here is we're going to drop a transmission line, this one right in here, and you're going to get a dip in frequency from the rest of the generating fleet until they can react fast enough to pick up that slack and pull the frequency back into normal operating conditions. This is what we would call a contingency analysis on the power system. So if we open that line up, there's a momentary dip in voltage across the middle of the Western Interconnect. The frequency dips down here. But the rest of the synchronous generators and the remaining wind power plants and utility scale PV ride through this frequency dip and pull the frequency back into 60 hertz range. And so a little bit further in the timeline, that's what you see, that this is still an outage condition on this transmission line, but the rest of the generators have restored the system operations. And that's an important thing as power system engineers. We need to understand what are the potential problems that you would see on the grid and how to make sure the grid remains stable with a variety of resources available. And we've done studies to show that easily we could maintain operational stability with 30% annual inverter-based generation in the western portion of the US. But remember, we're trying to get to 50%, not 30%. And we've done actually large-scale experiments using actual real power plants, both wind turbines and PV systems. This is an example of a 300 megawatt power plant that exists right on the Arizona-California border. An experiment we ran several years ago where we basically took this power plant and its normal output would be this green line here. But what we did was we actually reduced the output power by about 30 megawatts. And then we were basically giving what they call automatic generator control signal from the system operator. So there's a thing called the California system operator. They actually dictate large-scale power plants on how much power they should be producing. And by changing the real power commanded from the California system operator, we could show that this power plant could go both up and down very quickly. You can see here relative time in seconds. We were being given commands, and the output power of this PV system was going up and down, not because of clouds, but because we were commanding it to produce more or less power. The more or less power translates into system frequency and allows the grid to maintain system frequency. And we actually do this with all power plants throughout the entire grid right now, all large scale power plants, but we were demonstrating that you could also do this on inverter-based resources and that they could provide these services very quickly. Okay, so there are a variety of technical challenges with higher inverter-based resources. At NREL, we're doing a lot of work on trying to solve these challenges as quickly as possible, but they do require quite a bit of understanding of both the inverter-based resource capability as well as the power system. So I kind of walked you through stability. You know, if we didn't have any control of how fast those inverters were reacting, the change in normal frequency when an event happens can be pretty dramatic. But if we basically get into those controllers, have them recognize this change in frequency, we can actually create an actual much more stable system if the inverters are programmed to do that. Another part of this is system protection, and don't necessarily have time to dive into all the details of system protection, but the thing I'll point out is with this graph, which is that when you have a fault on a system, let's just say the fault is happening here, the output characteristics of a synchronous generator are shown in this blue curve. And you can see that the fault current is pretty high. In fact, it's about 6 times its normal rated output for a short amount of time. The problem is that inverters don't have that same 6 times overload capability. They only really can react about 1.1, 1.2 times nominal output. They can be programmed to trip very quickly, or they can ride through an event and then trip, but they don't have the same characteristics of a synchronous generator for fault current. And so things need to be adjusted or taken into account when you're operating grids with high levels of inverters. The other challenges you have is that you need the ability to actually completely restart the grid from a blackout condition. And typically we do that with batteries that start diesel generators that start power plants, and then we restore the grid. But if we're all inverter based, we need those inverter based resources to also have that black start capability. And then finally, we need to also look at how the control algorithms are developed in these inverters and make sure we're not causing undue system resonances or oscillations in the grid. If you program them correctly, you can actually improve this in the grid with these inverter-based resources. But again, the challenge is how are we able to do this with multiple different vendors, all providing different inverter technologies? So one thing that I'll also mention here is the difference between grid following inverters and grid forming inverters. The majority of everything that is deployed out there right now with wind and solar resources are typically what we call grid following inverters. They cannot make their own voltage sine wave. So this is an output of a typical inverter. What they rely on is the voltage waveform provided by the rest of the grid, and then they synchronize to that, and then they inject current or power into the grid. You would kind of consider this a follower. And what we're doing right now is trying to come up with the rules of the road of how to make all these inverters actually grid forming. So grid forming is used a lot on these small island power systems where we operate 100% renewables, but they're not really used on the larger grid. And that's something that we're spending a lot of time on recently, is how do we make sure that inverters really can be grid forming, that they can always be providing power, that they don't need to look for other synchronous generators to synchronize to and become leaders in this area. Because as we try to get towards 100%, we'll need more and more of grid forming inverters to be online. Just to show that, hey, this is real. We've actually done experiments at our laboratory. You can see a picture here where we interconnected a 1 megawatt battery to a 0.5 megawatt of solar to a 1.5 megawatt wind turbine. And we actually ran our building loads for 72 hours straight with just wind, solar, and battery. We actually experienced an outage at our site. So these are typically pieces of equipment that we're doing research experiments on, but we actually reconfigured them to run our native building load at our location outside of Boulder, Colorado. And if you look at the graph here, you can see the native load is this gray line, roughly around 300 kilowatts. It's fairly steady throughout the day. And then the solar energy produced is this orange line, and the wind is producing this green line. And then the blue is the battery system. So we're either charging, if it's below this level here, we're charging the battery, or we're discharging the battery. So all these three sources work in tandem with each other to power the entire load. And we were able to demonstrate that we could run 100% inverter-based grid for 72 hours, no problem. If we had a little more energy storage, about 6 megawatt hours, we'd probably be able to run the entire year based on our wind and solar profiles at the site. But that's what we did kind of on spur of the moment, just to demonstrate that we could do this and they could provide black start capabilities. So one of the things that we've recently started is this thing called the Unify Consortium, which really is designed around how to bring grid forming inverters into the power system. And the idea behind it is to really address the seamless integration and unify the operation of synchronous machines and inverter-based resources moving into the future. If you're interested in this and you want to learn more, we have like 25 seminars on grid forming inverters that you can find on our YouTube channel. Actually, if you just go to YouTube and look up Unify Consortium, you'll find our YouTube channel that's all about grid forming technologies. So that is kind of discussing, the shorter time frame, how we maintain operational stability with inverter-based resources. But there's a second challenge when you're dealing with wind and solar, and this is the one most people think about: the variability and uncertainty of wind and solar, and how do you start to balance the grid at longer time frames. So an example of that here is a picture of the United States with, that was the sun coming up, that line across, and yellow dots represent solar energy deployed. Now, this is a representation of the grid maybe in 2030 or 2040, where we have massive deployments of solar. Those are all those yellow dots, and here's the sun setting. That's being backfilled with natural gas plants, the pink dots. These green dots in the middle are wind. These lighter blue up here are hydro plants. Again, that was the sun coming up, all the solar coming online. And we've done large-scale analysis of how do you maintain grid reliability and balance all the generation and load with all this new variability being provided by wind and solar. These little spinning things to the side are telling you power flows between balancing areas in the continental United States. So this was part of several studies we've done. We actually, I'll mention one study at the very end of the presentation called the North American Renewable Grid Integration Study. That really looks at very high levels of renewables deployed across the US and demonstrates that what we need to actually operate the power system in that manner. So that's what we really need to do, is think about how do we create system flexibility that will enable more variable generation to come online. There's a variety of different types of what we were calling interventions, and I'll go through these in detail, a little more detail, that describe each of these system operations, the services from your renewables, how we do load control, flexibility of existing generation fleet, increasing transmission, and energy storage. All are ways to increase the flexibility of the grid, to add more wind and solar. Of course, they all come with a cost associated with them. So we'll kind of run through some of these. As I mentioned earlier, a lot about how do you take these inverter-based resources and allow them to provide voltage and frequency support, also the reserves necessary as we look out for maintaining adequate supply in the grid. But you also need to understand how much can your other resources that are online, hydro plants, gas plants, coal plants, how much can they ramp up and down? People normally think of things like nuclear plants and coal plants as baseload, running 24/7. And historically, we have run them that way. But we may need to rethink that ramping capability of these technologies, or come up with new innovative ways to tie them into other load functionalities. So it's important to understand how fast you can move these plants up and down in relation to each other. Another big piece of that most people think about immediately is, well, let's just add more energy storage. And energy storage is a great tool for handling some of this variability that you have from wind and solar. And I'll just explain the pros and cons of this. And in fact, since wind and solar have relatively low capacity factors, that means, during a 24-hour period, they may be only producing power 20 to 50% of the time. There will be an increasing need for some types of energy storage on the grid. Here's some examples of stuff that's out there today. This plant that you see in the left-hand side is a 250 megawatt for 1 hour lithium ion battery plant. So this giant thing right here is the battery, connects into this substation here and is used for load balancing. Now right now that's one of the biggest batteries in the entire world, 250 megawatts. But it's small compared to the largest pumped hydro system. So if you take a look at the right-hand side, this is the Bath County plant in Virginia. It is 3 gigawatts, so more than 10 times larger than the battery on a capacity basis for 11 hours. So more than 10 times on an energy basis. And you can see the plant here. There is an upper reservoir of water. There's a lower reservoir down here, and they basically pump the water between these two reservoirs. There's a great video on YouTube if you want to learn more about this pumped hydro facility. But there's not a lot of new pumped hydro being built in the United States. Mostly, as you can tell, it takes a lot of geographical area, and you need the right geographical places to do these types of systems, where you have a high reservoir, a low reservoir, and you can basically move all of this water back and forth in here. So you can't really use these a lot for recreation that you see on normal lakes. Some things to talk about when we look at energy storage. Currently, we have around 23 gigawatts of pumped hydro storage in the United States and around 1 to 2 gigawatts of batteries. And so we know kind of how much that energy storage is used across the United States. It's mostly used for about 8 to 12 hours of storage. But as we look at putting more and more wind and solar in, you can see these numbers really start to creep up. So now you're talking, we're going to need 100 gigawatts, and maybe once we get to multi-day and seasonal storage, 250 gigawatts of storage. So yeah, that's 10 times the amount of existing pumped hydro, or 250 times the amount of existing batteries that we have in the system right now. There are a variety of, it's not just pumped hydro and lithium ion batteries. There's also flow batteries, although none of these have really taken off to the level that lithium ion have. And we've looked at other things like using hydrogen storage. Again, no matter which technology you use, they cost money to implement. So there's that additional cost associated with adding energy storage into the system. Okay, some other things to think about. Well, I'll just say the energy storage in general costs money, and it costs a lot of money compared to some of the other options you have for creating system flexibility. So what are some additional options? One that we rarely tap into, but is out there, is the load or demand response. And there's a variety of different ways of looking at loads. These are typically, segregated into residential loads, commercial loads, industrial loads, and the up and coming electric vehicle load. So right now there's not a lot of electric vehicles deployed, but if we were to massively deploy electric vehicles, you potentially have options to charge and discharge electric vehicles to add that kind of capability. The challenge you really have with load is this: how do you actually control hundreds of millions of loads and generation and storage? Because for the most part, we operate the power grid by having a relatively small number, maybe 10,000 generators deployed across the United States, and we just ramp them up and down to meet the load. But load is also out there and available for control, even if it's small levels of control, right? Even if each house would only let you control about 100 watts or a kilowatt of power, you add all of those up, you get large amounts of demand response. So we've done some looking at how would we actually control these millions of devices. We did a big study where we looked at the Bay Area of San Francisco, you see it over here on the left, and deployed electric vehicles, building loads, PV systems. You could potentially have 10 to 20 million controllable devices in something the size of the Bay Area. And this is a little video of a simulation where we built the Bay Area as a grid. We deployed 400,000 solar systems as these yellow dots. We married them with 400,000 building loads in the Bay Area and 10,000 electric vehicles, the white dots, and charging stations, the green dots. And basically said, how could you actually control all these millions of devices? And if you're interested, you can dive into more details on this topic. Look up or Google autonomous energy grids. But we were able to demonstrate that through some clever ways of doing control, basically creating a distributed hierarchical control system, you could maintain operational stability and control millions of devices at 1 second time steps, which is basically what the utility does today, but they only really control about 10,000 or less generators at 1 to 4 second time steps. But this is an innovative way of really thinking about how do we create this future grid that has got controllability all the way into the load segments. Okay, some other ways to create system flexibility is just with the system operations of the grid. So things like this is better renewable forecasting, right? If we can do very good renewable forecasting, we can start to dispatch things on a fairly regular, on what we call sub-hourly basis. So historically, the power grid really kind of was set up in such a way that it dispatched generators a day ahead as well as maybe an hour ahead. But with the advent of more wind and solar, we've had to really tighten that down. Right now, places like SPP does this every 5 minutes. They do a forecast, they redispatch all their generation on 5-minute basis. And you can see they do a pretty good job of forecasting the actual wind output. The forecast is in green. Then the real output there is in red. Actually, that's a short-term wind forecast. This is really understanding a much closer as to, are they actually giving you the right values? And so these are important things to know, although I can see on here that this legend isn't entirely correct. This is load up here, and this is wind forecasting here. So they actually have a little bit of a misleading thing in their picture. But in general, we do a fairly good and accurate job of understanding the actual load and the forecasted load, as well as the forecasted wind dispatch. But there are things we can do to improve that. In fact, one of the big things we can do is expand the balancing areas. So what I mean by that is typically the balancing areas are where we try to balance load and generation. If they're small, the variability in the wind and solar can cause some big uncertainties here. If we can use larger areas to help move power around, we can actually reduce the variability that you would see from wind and solar. And that maps over to transmission. So if we can increase the balancing areas by expanding transmission and easing the ability to move power around the United States, we can then reduce some of that variability. And so we've done analysis. For example, if you don't know this, this is a good picture on the upper left, that the grid in the US is split into 3. The Eastern Interconnect you see here, the Western Interconnect, and the Texas system. We have very little power flow between each of these. They are run entirely as separate entities, all synchronized within each other, but these 3 are not synchronized together. So we actually have DC-DC back-to-back interties right now that run between those, and we're looking at what if we could increase the capacity of those power flows, either back-to-back or installing large-scale DC transmission lines between the areas to allow better power sharing. As you can imagine, since the United States has 4 time zones, the load is usually increasing as the sun is setting. But if you had something like this, you could be shipping solar energy during the middle of the day back to the East Coast if you had a way to do that. Right now, there's not really a way to do that type of load shifting, or overlaying an entire HVDC system on top of the entire grid is another option. So we've done analysis to look at these different deployments, and they come with different benefits. And of course, there's serious costs associated with such a large-scale transmission expansion. Okay, I wanted to hit on, if you're interested in diving more into this details, there's this thing called the North American Renewable Integration Study that looked at the continental United States plus Canada plus Mexico, all the interconnected parts, and looking at like 80% carbon reductions by 2050, how you would have to build out the grid and what type of deployments you would have across those areas. So some really great work to show that, yes, it's all doable. We just have to actually get motivated to get some increases in transmission and large-scale deployments of the renewable technologies. Okay, to sort of summarize things here, big thing is that we are really seeing this huge shift toward 100% clean energy goals across the power system industry, and each region has a variety of resources to tap in to meet those goals. But one of the biggest ways to address this is the increasing use of variable renewables like wind and solar. And the favorable economics in wind and solar are really driving new installations and deployments across the United States. Now, I hopefully highlighted the 2 big challenges we have with integrating this much wind and solar in the power grid. There's the inverter challenge of adding more power electronic-based devices, and sort of the balancing challenge with dealing with that variability at all time scales. at the end of the day, these are solvable challenges. There still needs to be quite a bit of work, but we think over the next decade that really these challenges can be solved, and then it turns into just a massive deployment challenge. So that kind of gives you an idea of where we think the entire industry is heading for wind and solar. And with that, I'll wrap up and say thank you. You can get a beautiful sight of out here in the Rocky Mountains and one of our test areas. And then there's more information here. I sent a PDF out to this, and you can pass that around if you want to dive into any of these things in more detail. So with that, I'll wrap up my presentation and take any questions people might have.
Thank you so much, Dr. Kroposki.
So, can you hear me?
Yes.
Okay. To what extent is gravitricity being used to store the wind and solar storage? Gravitricity, is that moving masses physically from a high height to a low height?
Yeah, I haven't actually heard that word, but I would assume that that's just moving large masses from one height to another height. In general, people have looked at using all sorts of ways of storing energy. There are hundreds of ways of storing energy. The key is to figure out, is it cost effective? It may be simple, like moving a big, I've seen things where people have put basically cars, rail cars full of rocks and dragging them up a hill and then letting them come back down to create electricity. All possible. It really comes down to the cost of these things and the locations, and the other piece, the amount of energy storage that we're going to need. So critical to think about those things on any type of energy storage.
So the next question, Joe, do you want to take the next question?
Sure. It's approximately how much power is lost when transmitting cross country?
Yeah, so in general, transmission systems nominally have 5 to 7% electricity losses in them from the transmission of power. It does depend on which specific thing you're looking at, but realize currently today we do not transmit power from coast to coast. It's only going halfway, but nominally it's around 5 to 7% losses.
So would it be fair to say that baseload switching to more on-demand operations would be cost prohibitive and cause them to shut down?
Potentially. It depends on the fuel types and everything else. For example, nuclear plants are still basically run base loaded. And where almost in all cases where we have nuclear plants, we foresee them running as base load, but since it's less than 20% or less, that variability probably is not going to come into effect at that level. Now, coal plants, on the other hand, definitely coal plants are a little more expensive to run than nuclear power plants. So they get cycled on and off and do more ramping with more renewables that are being put online. That is why another reason why you're seeing the really big shift of decommissioning coal plants and then retrofitting those locations with natural gas plants, because the natural gas plants can ramp much quicker than coal. So that is one of the many reasons that coal is also on the decline.
Okay. In an early slide, if I understood correctly, it referred to projected supply requirements increasing from about 1,000 gigawatt hours in 2020 to 3,000 gigawatt hours in 2050. For this projection, how much energy efficiency and demand reduction was included?
Yeah, so definitely some level of energy efficiency was included. Obviously, no demand reduction because the demand increased by 3 times. But the reason that you see that, and I may not have mentioned it. The reason why we're seeing that 3 times increase in demand is the electrification of 2 or 3 big sectors that use other fuels right now, mainly transportation. So the big shift to electrification of vehicles, especially the light duty vehicles or the automobiles that people use, and the electrification of building loads. So getting away from oil, fuel, natural gas as building heating elements and moving to electric heat pumps. So that big, massive tripling in energy use is all due to the electrification of other sectors that are not currently electrified. And by doing that, that basically reduces all of your petroleum use and coal, and we phase out natural gas or use some type of natural gas / hydrogen turbines into the future. But that big increase from 1,000 to 3,000 is electrification of non-electrified loads today. That really is we've done a lot of studies on this, but the way to get to carbon neutral or carbon free energy systems is to basically electrify almost everything. You're down to maybe aviation fuels and boating fuels, but you can pretty much electrify almost everything else. But that means you have to build a grid 3 times bigger than the grid we have today.
Is the electrolysis included in that analysis?
Yeah, there's some amount of electrolysis making the hydrogen that's going to run hydrogen combustion turbines into the future in that analysis.
So we're left with steel plants and cement plants and other high temperature applications in the industrial sector.
That's right, basically.
We have some more questions. If not, I have a question.
Sure.
I mean, the impact of this transformation of going from being a follower to a leader seems to be really, really important. Where are we on the technology scope of actually implementing that? And has that been done in these island situations?
Yeah, well, right now in the small island power systems, we have inverters that are leaders. We know how to make small power grids that operate with 100% inverter-based resources and manage stability and all the other power system problems. So that means we have the technology available, but those are almost always where you have a single manufacturer of a product. So, it's compatible with everything inside there. The way the power system works today is you can buy a synchronous generator from anybody and connect it into the grid and set it up and it'll work properly. That's where Unify Consortium that I mentioned, its main goal is to diverse in such a way that manufacturers would follow those standards, everything would be compatible, and the future grid would be easily to run. Today, if I had to guess, we're 5 years away from that. So we have a little bit of time to get, to still be deploying these grid following inverters. And that's okay. We should still be doing that as much as we can. And our plan is 5 years from now, we've solved the grid forming inverter challenge so that utilities can specify grid forming technologies to create that 25 to 30% of grid forming that we're going to need in the grid.
Interesting. So we have some more questions here.
Correct.
Joe, you want to take the next one?
Sure. If a small community is installing 6 megawatts of solar for roughly 1,000 homes, if they wanted to build in its own battery using water pumping up a 400-foot elevation change and micro hydro turbines to fill the demand gap during night and cloudy days, how does this compare to installing lithium batteries based lithium-based batteries, both economically and feasibly?
Boy, you want me to do a whole engineering study in one answer?
That's a
to
mouth.
the
That's a
question.
mouthful. That's a mouthful.
Okay. Let me just, I'll give you high level stuff without having, because there's a lot of details there that you would have to sit down and do a study on. First off, lithium ion batteries are currently pretty available and relatively inexpensive if you compare it to other storage technologies. They've built at least grid tied batteries are kind of riding on the coattails of the EV industry. So EV is really pushing the lithium ion batteries for their vehicles, but the grid people are getting to ride on that. So if you go out to Tesla cars, they use the same exact battery for their Tesla Powerwall systems that you'd find in people's homes or in their large power packs. I don't know which is more economical compared between a lithium ion battery based system today and what you could potentially develop on that type of that's a very small pumped hydro system that you would need two reservoirs of significant size, and you need pumping to go both ways on that. Again, you'd have to look at your conditions. Are you getting natural lakes involved? Are you having to build tanks? There's all these little details you'd have to consider to look at the economics between those two solutions. But that's a straightforward analysis. That's not too complicated. Somebody that understands this area could walk through that process of evaluating that. 400-foot elevation change seems reasonable for a pumped hydro type system. But again, it's the size of the reservoirs on both sides that are going to be the costly parts of a pumped hydro system unless you have natural reservoirs involved.
I mean, there are companies that are actually drilling holes in the ground to try and build a physical pumped hydro, right?
There are, so both pumped hydro with water, there are people that are using like a lake on the surface and using mining techniques to drill down and then tap into a lower reservoir that may be an aquifer and moving water between the two. That's something that's happening. They're also looking at just like mechanical up and down using an old mining shaft. Maybe you have 1,000-foot mining shaft and you can just move weights up and down. Again, you probably want to tap into any kind of either the reservoir or the mine or something. You don't want to pay a lot for it, and you would have to compare that to the cost of current lithium ion batteries. The one drawback with lithium ion batteries is they're really only designed around 1 to 2 hour storage. If you want 4 hours of storage, you probably need 4 1-hour lithium ion batteries all connected together. But they're really around 1 to 2 hour timeframes, whereas pump storage is usually longer timeframes. And if you're trying to design an island power grid or an off-grid system, usually you want at least 8 hours to, if not 12 hours of storage, typically on those types of systems.
Okay. The next question has 2 parts. One's a little bit political and one's a little bit technical. What % of the US electrical demand comes from Mexico? Is NREL providing any help concerning the trade dispute between US and Mexico? I'm not sure how those two link together, but.
Well, the first one is none. I'm pretty sure we have let's put it this way. We have electrical interties to Mexico and Canada. For Mexico, we do not export or import a large amount of power. They typically, over that interconnection, there may be a small amount just for balancing purposes, but we are not exporting large amounts of power to Mexico. As opposed to like Canada, we are importing a lot of energy from Hydro-Quebec, the Quebec area. So we are importing a lot of electricity from Canada. That's why we have to actually model that Eastern interconnect with the Canadian pieces in it. The Mexican piece, we don't really export or import a large amount of energy. Now, are we providing any help with the trade dispute with US and Mexico? I'm not sure about the answer to that question, because I don't really know which trade dispute we're talking about. But in general, we have done studies with Mexico on how they can add more renewables into their grid. But that's, of course, they have to build that and pay for that all themselves.
Okay.
And the next question is, how do fuel cells figure into the equation? And if not, why? Why not?
Okay. Yeah, fuel cells can figure into the equation. Fuel cells, you basically take hydrogen and oxygen, combine those together to create electricity and water. And in general, we don't have a ton of fuel cells out there because you need to create the hydrogen from something. But right now, the quickest way to create hydrogen is take natural gas, which is its chemical element is CH4. So natural gas or methane is CH4. You steam, reform that, you pull off the carbon atom, and you create hydrogen. But we don't really want to power fuel cells with natural gas. We have looked at electrolysis as ways to take excess wind and solar, electrolyze water, and create hydrogen. We have looked at every combination of that, and we have an active research project on both electrolyzers and fuel cells. So the technology exists. The big challenge is cost. Both fuel cells and electrolyzers are not cost competitive to the other technologies that I discussed here, especially wind and solar on $1 per kilowatt basis. Maybe they'll get there someday, and we're doing lots of research on how to get them there. But today they're not really cost competitive. So that's why we're not seeing a large scale use of fuel cell technology.
I'll take are there other questions, Joe? I don't see any.
Yes.
Oh, there
Yeah,
are?
there's a number of
Oh,
chat
okay,
questions.
let's keep going then. Okay. What role do you see for in-kind storage like heat or ice for those end use needs? So we're talking about thermal storage, basically.
Yeah, thermal storage definitely has a significant role in the future when we look at storage, because thermal storage typically is longer lasting. So make ice and then melt ice. We're doing experiments with various size levels of ice energy storage right now. Definite and thermal storage we see a lot in a technology I really didn't talk about called concentrating solar power. That's where you focus sunlight onto either a fluid or a molten salt. You store that heat. Both the ice storage and the heat storage technologies are nice because they give you roughly like 8 hours of storage, and they're relatively cheap. They're made of relatively cheap materials. The biggest challenge for concentrating solar power is the cost compared to photovoltaics is still several times more than photovoltaics. And in general, while good storage technologies, you still have to find their application. So if you have a good heat application or cooling application, then they match nicely to those. They're still. The problem with energy storage in general is it always costs money. No matter what technology you come up with, there is no free energy storage. And so people are always going to go with the lowest cost energy storage.
Okay, the next question, will recycling measures be developed at the same or better rate as the new materials required for renewables and legislated and enforced?
Yeah, so this is definitely something that both the wind industry and solar industry, as well as the battery industry, are taking into, they're discussing it. Let's put it that way. They know this is potentially a big problem because when you look at how much of this technology is going to be deployed and over the time frame, typically these technologies have 20-year lives. So 20 years from now, we're going to need to be recycling solar panels. We're going to be needing to recycle wind turbines. Definitely all of those industries have consortiums that are looking at the recyclability of those technologies. Are they fully recyclable? That is still something to be determined. Will it be legislated and enforced? That's an unknown question for me right now, because I live in the technology side, not the policy side. But it's definitely something that needs to be addressed. I mean, it's akin to, you know, why don't we have more nuclear plants? Well, we have a nuclear waste issue, whether we decide to recycle nuclear waste or we store it. Where are we putting all that nuclear stuff? Similarly with wind and solar, we have to think about, are we just going to fill up landfills with this stuff? Or are we going to be able to recycle these materials?
So this next question, Ben, is really enabling for NREL. There are a number of misleading articles or graphics floating around social media that imply that renewables will never be significant. Or another variation is that EVs are not clean because the power mostly comes from dirty coal and oil. Clearly, to us in the know, these are false arguments. Does NREL provide resources and/or media outreach to counteract these false narratives? Since most people are not tuned into the details, but are easily persuaded.
Yeah, I mean, obviously, from what I was showing you here, I mean, we are going to change the whole power industry in the next decade, and it will be much more clean based on wind and solar. And it will be what is charging your electric vehicles. You know, we do at NREL have some of that information available on our website. We're kind of in this gray zone where we are a technical research laboratory and don't do a lot of that policy outreach. We do some of it to dissuade some of those narratives, and you can find videos and other material on our website. If there's specific things you're looking for, I can see if we are doing anything in that particular area, but realize the majority of our funding goes toward research work and not toward trying to dissuade or debunk every crazy thing that's out there.
Thank you. Next one, Joe.
Do you know anything of progress in alternative utility scale battery technologies, particularly the iron flow batteries being developed by ESS Tech and probably others?
So I am definitely not a battery expert. I'll start off with that. There are a wide variety of new battery technologies that are being researched and evaluated. I'm not that familiar with the iron flow batteries, but I've seen a number of other material flow batteries over the years. So in general, there's lots and lots of chemistries, and each of them have pros and cons. When you get down to it, somebody at the company or in general has to sit down and do the economic analysis of, do they have all the materials that they need to get to some of these sizes that you see for the utility scale applications? And then can they really produce and manufacture these technologies for the cost levels that we're talking about? But in general, you know, we need gigawatts of capacity, and we need it to be ultra cheap. And that's why pumped hydro is such a popular storage technology for the utility industry. The problem is that most of the good pumped hydro sites have been tapped. And when we look at the different flow batteries, on paper, some of them look like they pencil out, but to me, it's like, show me one that is 10 to 100 megawatts in size, and then I'll start believing your technology.
So do you expect more government regulation? Oh, wait a minute, aren't the electrolysis predictions based on employing unused capacity at times of surplus generation to split hydrogen from water creating stored fuel with otherwise unused electricity. So basically
Yeah.
using hydrogen as an energy storage.
Yep, we have done a ton of analysis on that question. So there's lots of reports you can get off NREL's website that look at electrolysis, including some that I've written. But you're right. The key thing for electrolysis to work is ultra cheap electricity. And you're going to find ultra cheap electricity when you have too much wind or solar on the grid. But there are many hours in the day in SPP service territory, that one that I showed you, with when they have massive amounts of wind at night and not enough load, and they're basically zero cost electricity. So depends on, you know, all the capital costs of the electrolysis equipment, but I don't think that cheap electricity is going to be a problem. You will have lots, when we deploy as much wind and solar as I was discussing, you will have lots of times in the middle of the day with solar and lots of times at night with wind where you will have almost zero cost electricity.
You also have the seasonality, right? I mean, they're
Yes.
going to have loads and loads of excess capacity in the summertime, and if you're going to have enough in the wintertime to manage the demand.
That's right. You're going to have seasonality ends up playing a very big part when you get to these ultra high levels of renewables. And it really is locationally dependent, but you are going to have significant amounts of time where you have super cheap electricity and you're going to want to store it.
Get the next one, Joe.
Sure. Do you expect more government regulation to guarantee variable sources come online and fill in the gaps? And the second part of that question is, or will the local grid regions still have to operate on price incentives? Just trying to understand the power purchasing direction given the industry desire for profit.
Right. You know, a lot of the government regulations are very much dictated by whoever's in office. Those change and go up and down, and there's more or less support behind them. At the end of the day, if you can make things economical, that is going to rule all bets. Because if you're making ultra low cost electricity from wind and solar, that all of a sudden is going to just change the dynamics of everything. And so I think personally, we'll see less regulation requiring this stuff, and the utilities will just start, and they're starting to see the light that, oh, these things are cheap. They can help reduce rates in general, and we need to deploy more of these technologies. We're definitely seeing that out west. My local big utility here is called Xcel Energy. They have fully gotten on board with renewables. They're phasing out their coal plants 10 years quicker than they thought they would. They're just going straight to wind and solar and getting this stuff into their grid as fast as they can because they're seeing the economic benefits of the technology right now. Of course, we have fantastic wind and solar resources here in Colorado, and there is about to be, I didn't really talk about offshore wind, but there is about to be a massive deployment of offshore wind in the mid-Atlantic and Northeast regions. And you're going to see that extremely low cost wind come online in the New England, New York areas. So I think economics really is going to drive everything at the end of the day. It's nice to have these lofty goals one way or another, and I don't know how fast we're going to reach any of these goals, but the technology today is cheap enough that it's going to start dominating, and that's what matters.
And the power electronics technology, the number of engineers, electrical engineers that can do this are sufficient to build out this evolution?
Well, that's a great question. I mean, I am actively involved in the education of power system engineers. I teach at University of Colorado Boulder. We could use a lot more is what I could say. I'd love to see a lot more homegrown people. We have tons of people from around the world that are in the programs right now, but we really have, basically an aging workforce in the electric power industries right now. And we're having this massive transformation, and we need as many new minds as we can to get involved in the power system, power electronics, and renewable sectors.
Okay,
We have one more question here.
Yep.
Current status of coastal tidal electrical generation.
Yeah, there are devices under test. They're relatively small. They are not going to outcompete wind and solar in the next 20 years.
Can you provide a timeline estimate of those offshore mid-Atlantic wind resources coming online?
Yeah, there's a massive study underway right now, funded by the Department of Energy, looking at the offshore wind build out, both where to put all the turbines, how do you get them, how do you get that electricity back to shore, what technologies do you use? That is over the next 20 years is when all of that build out will occur. There's a few small plants off of Rhode Island today, but they're getting ready to just put in gigawatts of wind offshore all along the northeastern seaboard in the next decade. It takes a while to do all the planning for these big plants, but when they go in relatively fast. You can put in hundreds of megawatts of wind and solar in under a year, which if you compare that to building a new coal plant or nuclear plant is extremely fast.
That's because these individual turbines are now 12 megawatts. That's what
Right.
they're planning on putting out on the ocean. 111 of them are in this Atlantic Wind Shores project.
Right.
It's incredible. I mean, and they're supposed to be online 25, 26, 2025, 26.
Right. So within the next 5 years, there will be a massive deployment of offshore wind along the Atlantic coast.
Are there any other questions from the audience here? Going once?
I have a quick one. If you
Go
can you
ahead.
hear- Can you hear me?
Yeah,
Yeah,
go
just
ahead, Al.
there's been a lot of discussion over time about electric cars becoming sort of time shifting devices for storage. Also, is that still considered to be a major resource?
Yes, definitely. When we think about electric vehicles and the deployment of electric vehicles, there are some important things to think about from the power system perspective. Like number one, we definitely do not want everybody coming home and charging simultaneously. If you do that, we will be creating massive problems on the grid. One of the reasons the grid works so well now is diversity of load, people turning on and off things all the time, and it kind of averages out. If everybody comes on and slaps on a load that's equivalent to their entire household load, these home chargers are basically equivalent to that, pretty much simultaneously, 5:30 every night, you're going to have issues. So we need to actively think about what we need with these electric vehicle deployments. We need them, you want it fully charged, or you want it charged to a certain level by the time you leave in the morning, but it doesn't all have to happen from 5 to 7 p.m. It could be happening from 2 to 3 a.m. when there's excess wind, as an example. So I'm still concerned because I haven't seen really the utilities step up and work with the vehicle charging manufacturers to come up with a strategy of how you mitigate all of these charging electric vehicles. On paper, yeah, we can do it, but the reality is, wow, how do we actually make it happen? You're on mute, I think.
Al, you're on mute.
Sorry, I
Good.
got it. I think now.
Yeah.
Yeah, we actually do the same goofiness with our everybody going to work at the same time, right?
Right.
And we haven't been able to solve that for I don't know how long, although I still don't know why. But it would seem like, like charging while you're at work when the solar power is peaking and you're not driving seems very, very logical. And then that could be used overnight or whatever. I mean,
Right.
I can't figure it out, but
You just have to put chargers everywhere, basically. I mean, at NREL, sure, we're lucky and we do a lot of research. So we have chargers for a lot, and we have a lot of people with electric vehicles, and we have chargers at work. So yes, we have done analysis of all those kind of things. But if you just don't take any accounting for it, you're going to end up in trouble. So
Can
some
I-
people need to
can-
think about it.
Can I add a little something to that? I have an electric vehicle that I charge that has a device that you can set the charge for 3 in.the morning
Mhm.
and just do that for every day, or 4 in.the morning, whatever. And the other thing is that I'm using a 110 line. I originally had a fast charger and it sort of went out of commission, and I just plugged it into 110 and that's working really fine, which
Mhm.
was much lighter load, excuse me, load on the system.
Right.
But I imagine that all electric cars will have the ability to just set it to charge only at 3 a.m.
Yeah, and so then I see a comment from somebody that says they're required to charge at midnight. That's good, and hopefully everybody follows all those things. And maybe we even have smarter cars that are sitting there listening for a signal from the utility that says, "Hey, electricity's really cheap right now. Whoever wants to charge, you should go for it." But we do have to. The utilities have to think about how do you make that more effective.
Sure, absolutely.
The other thing I would point out is that if everybody charged at 3 a.m., we probably would have a problem, right? So you do
Right.
need to figure out how to spread all that charge out.
That'd be, yeah. Maybe there could be I know that for my car, there's sort of a Pennsylvania a club
Mhm.
where people talk to each other, and maybe they could sign up for certain times a day.
Right.
I've had enough years of rush hour. I don't want rush hour on charging the electric cars.
Right. Right. But I'm sure it'll work out, but I see the problem, that it could be a big problem.
Mhm.
You want to end with one comment about the role of microgrids, Ben, and this whole
Sure.
scenario of local versus large distribution systems?
Yeah, so I didn't really touch on that. I kind of talked at a high level, the big picture of energy and electricity in the US. And I completely think that the big utilities need to get on board with utility scale wind and solar, because if they were all providing you clean electricity, maybe you wouldn't need renewables or solar panels on your house. But there is the one little thing about microgrids and improved reliability with having some of these distributed generation sources locally. We've done a lot of work looking at what it would take, for most people to have individual household microgrids or campus-wide microgrids. And again, you have to weigh the cost benefit ratio between the added cost of adding these generation and storage technologies to your location with the cost and the improvement of reliability that you get from having those. So if you had a lot of blackout or down power conditions, then you may want to definitely consider some of these microgrid type applications. But it's definitely something to consider, and maybe into the future, depending on the cost of these networked microgrids that can power larger areas.
And then they have to have leading capability with this inverter technology, right?
That's right. Right. Once you switch to that microgrid mode, those inverters now have to be grid forming to operate the grid
That's really
inside those
interesting,
areas.
really important. Thank you. Thank you so much for giving us this presentation tonight. And really think everyone got a lot of useful information from it.
Good. I'm glad you enjoyed it, and it's been a pleasure talking with you today. And the rainstorm has passed over on this side, so we made it the whole way without the internet crashing, which is great to see.
Thank you so much. And if anyone wants to stay on for informal chat afterwards, just stay logged in. And we thank you so much for your presentation, Dr. Kroposki.
Okay, thanks a lot. I'm going to take off now, but it's been great
All
talking
right,
with
thank you.
All right, thanks. Bye.